Hello folks, here's another video about Eelco Dolstra's PhD thesis for Nix. More Dutch PhD theses. I'm excited. So in this episode, I'm going to talk about chapter 2, which is an overview of Nix. And for the most part, I think we're going to pretty much just limit ourselves to 2.1, the Nix store. And this will cover pages 19 through 24. We're going slow, man. We're going slow. So in the previous episode, we went over the sort of summary of his thesis, and now we're going to go on to chapter 2, an overview of Nix. The Nix store, as we saw in the last video, Nix is a system for software deployment, and in this chapter, Eelco defines what a component is. He hadn't defined it up till now. He says he's going to use it to denote the basic unit of deployment. And as far as Nix is concerned, a component is just a set of files in a file system. What we call a component typically corresponds to the ambiguous notion of a package in package management systems. Nix's notion of components is discussed further in section 3.1. We won't get there. Nix stores components in a component store, also called the Nix store, so /Nix/store. Each component is stored in isolation. No two components have the same file name in the store. Eelco refers to this figure, and he is highlighting that the root of such a component store is /Nix/store, and then within that /Nix/store, we have individual components which are identified with a cryptographic hash and then a descriptive bit here. So here we have hello, glibc, subversion, OpenSSL, subversion, OpenSSL. The closure, meaning all of a top level component plus all of its dependencies, is here, I suppose. So subversion depends on this version of glibc. This version of subversion depends on this version of glibc, and within itself, it also has a dependency on itself. Within this, it has a dependency on that file within its own component, and then subversion also depends on this component, which is OpenSSL. This version of this component, and the point of it is that this version of subversion does not depend on this version of OpenSSL down here. Its closure does not include that version of OpenSSL and does not include hello up here. So it says the initial part of the file names, e.g., the BW, ACC, et cetera, is what gives Nix the ability to prevent undeclared dependencies and component interference. It is a representation of the cryptographic hash of all inputs involved in building the component, which I think is pretty important. I imagine we'll talk about that at length. Cryptographic hash functions are hash functions that map to an arbitrary length input onto a fixed length bit string. They have the property that they are collision resistant, et cetera, et cetera. I think we know if you've ever used an MD5 hash or an SHA-256 hash against some amount of content, you know what this is. Nix uses 160-bit hashes represented in base 32 notation, so each hash is 32 characters long, and some of them are abridged. A store path is a path to a component. The store path also contains the cryptographic hash, but also has a little bit of stuff after the cryptographic hash that describes what the component actually is. And this hash, the BWACC7A5, etc., is computed over all inputs. So this includes the sources of the components, the actual bytes that make up the source of the components being built, the script that perform the build, the bytes of the script that perform the build, and the arguments passed to the build script or environment variables involved in the build. It's their bytes, and all build time dependencies, what their cryptographic hashes were, I presume, including compiler, linker, libraries, Unix tools, etc. And the point of this is to prevent interference between components so that when you install something, you are not breaking some other subsystem on the system, or if you remove it, you're not breaking some other subsystem on the system. And they allow complete identification of dependencies, which I think we'll talk about in a second here. So he says the lack of these two properties is the cause for the vast majority correctness and flexibility problems faced by conventional deployment systems. So he's talking about why the hash prevents interference. When he says interference, he just means messing with other things that are already installed on the system. Since the hash is computed over all inputs to the build process of the component, any change, no matter how slight, will be reflected in the hash. This includes changes to dependencies. The hash is computed recursively. So I don't exactly know how this works under the hood, but I think for any given component, all of its inputs, all of its direct inputs, its source, the environment, and the arguments passed to it, and the actual Nix script that actually does the building, or at least the AST of such a thing, is reflected in its own cryptographic hash. But also what's reflected in its own cryptographic hash is a hash. This is the way I'm thinking about it. I don't know if it's implemented this way, is a hash of the cryptographic hashes of all the components it depends on. So it's not just the stuff that goes into the thing being built. It's that the hash also takes into account all of the hashes of the things it depends on, the components it depends on. It's essentially a unique identifier for some configuration, not only of the build flags for this thing, but of all its dependencies. So if two component compositions differ in any way, they'll occupy different paths in the store. Installation or uninstallation of configuration will not interfere with any other configuration. So the closure of one thing can be installed without blowing something away that's in another closure. All right, so for instance, in the Nix store, in figure 2.1, there are two versions of Subversion. They were built from different sources, so their hashes differ. So let's take a look at that. Here's one version, and here's the other version. One thing I think is interesting about this is that these have different version numbers, but the version number really isn't the input that is differing. It is the contents of the source that are different. That's differing. That makes Nix think that these two things are different. They might have the same version number, but that doesn't necessarily mean they're the same. So, yeah, sorry, that's my editorializing here. Okay, it says, additionally, Subversion 1.2.0 uses a newer version of OpenSSL. This newer version of OpenSSL likewise exists in a different path from the old OpenSSL. So even though the other Subversion depends on some instance of OpenSSL, when we install the new version of Subversion into the component store, it's not like we overwrite the old version of OpenSSL. It's a different version. They're both installed at the same time. Recursive hash computation causes changes to a component to propagate through the dependency graph. This is illustrated in figure 2.3. These are the sources. These the square boxes are sources. The round boxes are components that are built from those sources. The square box here results in this particular component when it's built, and on the other side, we basically upgraded GTK plus 2.2.4 to GTK plus 2.4.13, and as a result, the way we said we wanted GTK 2.4.13 was by changing Firefox here. So it says Firefox 1.0, and we said, go get us source for GTK plus that is at this, probably this Subversion revision, at this time it's 2006 or so, and on this Subversion branch or whatever, that is the version of GTK that I want you to use. And before that it was 2.2.4, and after that it was 2.4.13, and we can see that what he's saying is that the change propagates through the tree here. This isn't a great example of propagation because it's only one step deep. But yeah, so the point is that the hash of Firefox changes after all this stuff too. It's not just like we go get a new version of a GTK and it happens to be compatible and we don't have to change Firefox at all. It's not like we go upgrade GTK behind the back of Firefox and the old Firefox keeps working, we make a new version of Firefox that depends on the old one. Yeah. And the corollary is that components that don't depend on GTK don't get affected. Upgrading only happens by rebuilding the component in question, and all components depend on it. We don't replace anything in the graph. It's never destroyed until garbage collection time. Thus, he calls this a purely functional model. The build time inputs determine the contents of the component. So in purely functional programming, languages such as Haskell, and in mathematics, the result of a function call depends exclusively on definition of the function and on the arguments. That is what the definition of purely functional. It says in Nix, the contents of a component depend exclusively on the build inputs. The advantage of purely functional models is that we obtain strong dependencies about components such as non-interference. And I think one of the sort of unsaid things is about this. It's not unsaid, it's just implied, and I'm sure he talks about it. But I find that oftentimes, like, that people just have failures of imagination. For example, I'll just give you an example. I write lots of, well, depending on what you think lots is, I write Python software. And my baseline for shipping software to a customer is that it has 100% line coverage in tests. So when you run the test suite, all of the code that I wrote is executed at least once. And that is required, but not sufficient to test the code. I also write functional tests. Does it actually work? It's not enough to know that all the lines are covered if the tests don't actually exercise the functionality of the stuff. And many people think this is absolutely ridiculous. They can't imagine doing such a thing. And I think my take on it is that it is a failure of either my imagination or their imagination that we can't sort of come to terms about what it means for software to work. So when I come up to them and I say, yes, I'm going to write enough tests so that all the lines are covered, they stare at me. Often they'll stare at me blankly, and they'll just be like, wow, like, I don't think so. And I'm like, no, that's really what I'm going to do. Yeah. And so in this thesis, one of the underlying things that is most problematic, I think, about this is that when you build a component that's way down in the graph, then you have to rebuild all the components that depend on it. If there's some security problem or whatever, and you have to upgrade something that's way deep down in the graph, you have to recompile all the stuff. And that's just, yes, you have to do that. Yep. There are ways around this in Nix, replace runtime dependencies and stuff. I've never actually used them. I don't even know if they work, to be honest. He says that they also prevent the use of undeclared dependencies because they don't live in a global place. It's harder to mistakenly put them on the path of something that needs to find them. He's talking about at build time, and then at runtime, he says we have the same problem. Since components can perform arbitrary I/O actions, they can load and use other components. Of course, there are countless mechanisms other than static or dynamic linking that establish component composition. Some examples include C header files, importing Java classes at compile time, calling external programs found through the path environment variable, and loading help files at runtime. The hashing scheme neatly prevents these problems by not storing components in global locations, but in isolation from each other. For instance, assuming that all components in the system are stored in the Nix store, the linker line gcc -o program main c uic l ssl will simply fail to find libssl unless the path to an OpenSSL instance is explicitly fed to the build process and add to the linker search path. No such instance will be found by the linker. And I imagine we'll go into it a little bit later that when things are compiled under NixOS, the GCC that is used, the GCC command, is not really the GCC. There it is wrapped, and the paths to the dependencies that are declared in the build dependencies, native to build dependency, propagated to build dependencies, whatever, are actually put into the linker path. that is how they're found. Nothing that is not explicitly put into the path of, or into the environment is considered to be a dependency. Go to some links to ensure that component builders are pure. Yeah, so he says the builders call with an empty set of environment variables. When you run nix-build something or other, it's not like the environment of your shell is fed to the component being built unless you arrange for that to happen. We use a patch dynamic linker that does not search in any default location. So if dynamic library is not explicitly declared within its full path and executable, dynamic linker won't find it. So user lib, not on the path. Yeah, all those things are not on the path. Only the things that are fed to it. And what he's saying is the deployment of the systems discussed in section 1.2, which we talked about in the last video, allow components to do that. So because they have the global paths on there, the build system may run successfully even if some dependencies aren't declared. He talks about retained dependencies. Now, I'm in a little over my head here. When you tell Nix how to build some software, and particularly if you give it dependencies that are shared libraries, .so files on the file system, often paths to those shared libraries will end up in the ELF binary, in the rpath section of the ELF header of the binary. And apologies if I'm just using the wrong wording there. This is there are a lot of details here. I'm not even sure rpath is the right term. When you create a binary, an ELF binary, often in a certain section of the binary, there will be a path to a .so file or some shared library. That is another way that components can be linked together. The reason I'm dithering here is that I'm not sure under which circumstances this would happen if you didn't already supply the builder with a build input. That, like, could it be possible that would end up in this ELF if glibc was not a build input already? So you would know about the build input, but this, even though our patch link dynamic linker does not search blah 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 blah, by default it will find the library anyway through the executable's rpath. This might appear to be bad news for attempts to prevent undeclared dependencies, but how would it have found it if it wasn't declared? I don't quite understand. All right, let's read it again. A rather tricky aspect to dependency identification is the occurrence of retained dependencies. This is what happens when the build process of a component stores a path to a dependency in the component. Okay, a path to the dependency in the component. For instance, the linker invocation above. This one, GCC. The linker invocation above will store the path of the OpenSSL library in a program, i.e. program will have a hard-coded reference to that. Will it? Let's see. Why? Why is that true? Don't you need to pass in -rpath? Yeah, I'm confused about this. Okay, let's presume that I'm wrong, and the linker invocation above will store the path of the OpenSSL library and program. I think maybe what he's talking about here is that GCC, native GCC wouldn't store the path in there, but after Nix does all its magic of wrapping GCC, it would store it in there. I think that's what maybe that's what he's talking about. Right. So it says figure 2.4 shows a dump of parts of the subversion executable stored in the file, blah blah blah, and the path of the OpenSSL has been stored in the rpath field of the header of the ELF executable, stored in the rpath field. Path of OpenSSL. Okay, so what are we storing? OpenSSL. Oh, okay. It's not just the full path to the actual .so file. It is a path to /lib of OpenSSL. Huh. Oh, okay. I think I understand. Yeah. Okay. Sorry. Just hang in there. What I'm trying to make sense of is the difference between what he's going over here, these retained dependency things where a path to another component is jammed into, the header of the binary or whatever. I am unsure about the nuances of when this is desirable and when it's not. I would presume that the linker would be the culprit of putting such paths in the binary. And if it were to put such paths in the binary, it's because some component that is in Nix told it to do so, but then we have to go back and scan again for things that we have to scan, and he's saying that we can see that something in these binaries has a hash, that this 32-byte string, and therefore we can change some portion of that, or not necessarily change it, but we can scan for unnamed dependencies. But I don't know how the dependencies would have been unnamed if they were found by the linker in the first place, because we would have had to told them where they are. So there's a bit of Spider-Man meme thing happening here that I don't quite understand. Maybe we will figure it out in later bits. So anyway, he's saying that if as part of a step later in the compilation process or in the component creation process, I think where this lives is actually in the fix up step that you see that's in builds of Nix things. And what it does is it goes and scans for hashes everywhere, not just in binaries, but in the docs and everything. And if it finds a hash, something with this composition, this 32-byte composition that's in certain format, then it includes that as a runtime dependency. Maybe that's the difference. Maybe in the Nix stuff we name build time dependencies, like we say build inputs. Yeah. Okay. It's coming back to me. Okay. So we say, in order to build this piece of software, we need these components, and that's why OpenSSL winds up inside this RPath. But we don't need all the build inputs at runtime. So the scanning stuff actually says, okay, start with a clean slate. I think, like, we'll find out. But start with a clean slate. We don't need any runtime dependencies at all. All we have are build inputs. The scanning stuff goes through all of the produced binaries and artifacts that are produced by the build process, looks for these things that are inside the binaries and the docs and whatever, and picks out the stuff that the result actually depends on at runtime using these things. So OpenSSL is dependent on at runtime. We know it's dependent on because one of the binaries has this in its RPath. That's my final answer. I think that's how that works. So I wish he actually said that. I could be wrong. Yeah. I wish he actually said that. I could be wrong, but that's what I'm going with for now. That's my understanding. Okay. So he says, strictly speaking, it's not the use of cryptographic hashes per se, but global unique identifiers and file names that make this work. So he's saying that because we can scan for these things and we find some identifier that matches our format, we know that it's this component over here. But he says the hashes are needed to prevent interference, which is what it does. But at the same time, random things aren't good enough because we would have unnecessary duplication of things. So, okay. So in our last video, and we talked about first day, the goal of complete deployment. Safe deployment requires there are no missing dependencies. Okay. And this is where we talk about closures. I think I mentioned the word closure before, but it is just a piece of software and all of its dependencies and all of their dependencies and all their dependencies, etc. That is when we copy a component X to client machine, X depends on Y, then we also need to deploy Y, whatever. What he's saying is it's not that Nix says, Nix's interpretation of Firefox says it depends on this version of glibc. It depends on this version of glibc where the contents of that version of glibc generate this cryptographic hash. The contents of glibc plus the recursive cryptographic hash of all its dependencies and so on and so forth produce this hash. It's basically about the content, not necessarily about the version number like about other things. Both at build time and at runtime, Nix knows the dependency graph. And it can compute the closure, everything required. Figure 2.2 shows closure conversion 114. Okay, so he's going over some bad sides of the purely functional model. Hashes do not appear to be very user-friendly. They are not. Can we deploy upgrades efficiently? That is, suppose we want to upgrade glibc. Can we prevent a costly redownload of all dependent components? As we'll see in the remainder of this thesis, the answer to the question is yes. I'm looking forward to seeing that. And I think that's all we have time for today. Sorry for going so slow here. I'm learning. All right. Thanks for watching, folks.